No.
Okay.
Okay, so welcome everybody to class. Thank you for coming, as always. I started the recording now, so if you want to type your name into the chat now, it will get recorded. If you typed it in before I started recording, then it will not be recorded. So if you did it, please type your name in one more time so that I have a full record of the attendance. All right. Thank you. Okay, I'm going to just put everybody on mute. So that we can hear more easily. I'm good. How are you, Saley? Or how, Christopher? How are you? Okay. Okay. So welcome again to everybody. For what is
Hello,
our
Andrew.
hello, hi, Christopher. How are you? Is it Christopher? That's I don't know who's talking.
I'm fine. I'm fine.
Okay, good. I'm glad you're fine. Okay, is this Gabriel or oh, Gabriel. Hi, Gabriel. Okay. Welcome everybody. So I'm just gonna mute. So just before we start any math, I want to just remind everybody that this is the last class of the year. So it's not the last class of the term, but the next class is going to be in 3 weeks. So the next class is January 6th because we have Christmas next week and then New Year's the week after. So this is going to be our last class until January 6th. I'll send another reminder about this at the end of the session. Okay. So so welcome again to everybody. And what I want to do is talk a little bit more about these determinants today. And then also talk a little bit about cross products and how cross products and determinants are related. And then what we'll do next time is discuss the geometry involving cross products and determinants. Okay, so as usual, I want to go over the homework problems first. So there were 2 problems that were both kind of the same problem, which were asking you to write down a 3x3 matrix that gives a certain geometric transformation, right? So the first question was, if XYZ is reflected over the XZ plane, what is the result? And then if we know this, can we write down the 3x3 matrix that corresponds to reflection over the XZ plane? And then part 2 is the same question, but for the YZ plane. So let me just divide the space up into 2 parts. So we have this side is going to be the XZ plane, and this side is going to be the YZ plane. And if you recall, we did this example for the XY plane at the end of class last week. Okay, so so for the XZ plane, we want to know if I start with the vector XYZ and then I reflect it over the XZ plane, then what's the new vector that I get?
Hello.
Hello, yes. Tomas? Or Gabriel? Sorry, I don't know who asked to answer, either Tomas or Gabriel.
I'm not getting what you're saying. Please come again.
Okay. Sorry, Tomas? Okay, sorry. Hello, yeah. Yes, Tomas? Or Gabriel? Gabriel, there's a lot of background music coming, so I can't hear very well.
Okay, they are meeting in that direction.
Okay. Do you want to answer the question?
Meeting in that position.
Okay. Sorry. Okay. Yeah. Okay. I can't hear that well. Sorry. I'm just going to mute. Okay. Sorry. I wasn't getting you. I couldn't hear so well. So, okay. So we take the vector XYZ and we want to reflect it over the XZ plane. If I want to just draw a little picture, this is X, this is Y, this is Z. The XZ plane kind of looks like this, right? So we're reflecting it over the XZ plane. So if I have a certain vector here given by X, Y, Z, sorry if that's written very small, if I want to go take its reflection, which is going to be reflected over the XZ plane like this, what are the coordinates of the new vector that I get?
Yeah, I think the
Yeah,
coordinate will be, I think the coordinate will be x, 0, and z.
So, okay, so X and Z are definitely right? So X and Z will stay the same, but we're going now from this Y coordinate on one side of the XZ plane to a Y coordinate on the other side, right? So it's not going to be 0 because 0 would put it right on the XZ plane. But what are we actually going to get instead?
Negative y?
Negative Y, exactly. Right, so we get negative Y. So right, so X, Y, Z goes to X negative Y and Z. Okay, and so what we want to do now is fill in what matrix when we multiply it by X, Y, Z is going to give us X negative Y and Z, right? And so what we've seen before is, well, we have the identity matrix that if you multiply it by X, Y, Z, you just get X, Y, Z again. But if we want a negative Y instead of a regular Y, what do we have to change about this matrix?
Yeah,
Yep.
you're negative 1.
Yeah, so which one becomes negative?
The last one.
Careful, right? We want
In a chair, in a row.
yeah, so which one of these
in a row will become negative.
right. So what we
The
need
last one that is there.
yeah, so sorry, I'm not hearing so well. So there's these 3 ones. Which one do we need to make
Hello?
negative?
Yeah.
I said,
Yep, Gabriel.
Yeah. We will move to the middle one.
The middle one.
the middle one. Okay. Yeah.
Exactly. Great. Thank you. Yeah, the middle one, right? Because if you do the matrix multiplication here, you're going to get an X in the first row, and then a negative Y in the second row, and then a Z in the third row. Okay. Okay, great. So we do this, we make a negative 1, and this matrix here with 1, negative 1, 1 along the diagonal is going to represent reflection over the XZ plane. Okay. And for the YZ plane, we have something very similar, right? We have XYZ is now going to map to, well, let me just draw the YZ plane now. If I have X, Y, and Z, then the YZ plane really just looks like this, right? This is the YZ plane. And then if I have some vector like XYZ, which is a little bit hard to write, maybe let me draw it a little differently so it's less cluttered. So if I have some vector here, which is going to be given by XYZ, then its reflection, if we think of this one as kind of pointing out of the board, the reflection is kind of going to point into the board or into the paper. And this is going to be its reflection. And what's going to change? Well, the Y and the Z coordinates stay the same, but the X coordinate is now going to change because it's now kind of pointing into the board. So this is going to be negative X, Y, Z. So X, Y, Z is going to go to negative X, Y, and Z. And so if we want to know what's the right matrix, well, if I multiply this identity matrix by XYZ, I just get XYZ back again. But now if I want to instead get negative X, which one do I need to change to a negative?
First row, first column.
The first row, first column. Exactly. So that becomes a negative 1. Okay, so these are the matrices that give us the reflection. Here I have 1, minus 1, 1 down the diagonal. And here I have minus 1, 1, 1 down the diagonal. Okay, so this is the first 2 homework problems. So these matrices give us these reflections. Now you can ask also, how would you do a reflection around a plane that's kind of diagonal, that isn't just with the coordinate axes? So that's, quite a bit harder, and we're not going to do it right now. But if you want to talk about it separately on the chat or something, then I'm happy to discuss how we do that. Okay, but before that, any questions on these 2 problems?
Yeah, sure.
Yes, Prince?
Yeah, Let's say, for instance, in case a vector was going to come down between the x and the y. So
Mhm.
which one are going to change there? Which one are going to change?
Right. So it
And how
doesn't
much the
matter.
vector going to be?
Yeah, so it doesn't matter what vector you have. Wherever, I mean, I just drew these vectors as examples, but whatever vector you draw, let's say in the first example, if you're reflecting it through the xz plane, it's always the y coordinate that changes. So the y coordinate will always become negative, and the x and the z coordinates will always stay the same. And same thing with the yz plane, no matter what vector I draw, the x coordinate will always become negative and the y and the z will stay the same. And then the example we did at the end of class last time is if we reflect it over the xy plane, then the z coordinate changes and the x and the y coordinates stay the same. Okay, but that example we did at the end of class last time.
Oh,
Okay. All right, any other
all right,
questions?
thank you.
Okay, you're welcome. Okay. Any other questions? Feel free to just ask. You don't need to raise your hand.
Yeah,
Yeah, Princeton?
yeah. So we have the first one S and Z plane, and the
Right.
second one Y and Z plane.
Right.
If we were having S and Y plane, so how will the coordinate be?
So okay, so this is what I said before. If it's the XY plane, what you get is instead of XYZ here, you would get X, Y, and minus Z. Right? The Z would become negative. And what would happen with the matrix is that you'd have a 1 here and a 1 here, and then a -1 in the third place in the lower right. So otherwise it would be the same, but the -1 would be in the third place. And you'd have X, Y, and minus Z.
Thank you.
Okay, you're welcome. Other questions? Okay, so let's just do quickly homework number 3. Question is, what is the determinant of the 1x1 identity matrix I1? And what about the 2x2 identity matrix I2 and the 3x3 identity matrix I3? So remember, I'm just going to write down these matrices. Okay, and so maybe before we answer it, let me just recall that we finished up last time talking about determinants of matrices, right? And so we said that for a 1x1 matrix, the determinant is just the entry in the matrix. For a 2x2 matrix, the determinant is given by multiplying A and D and multiplying B and C and subtracting them. And so this is our determinant. So this is our example. If you have 1, 3, 7, 9, you have 1 times 9 minus 3 times 7. So the determinant here would be -12. And then lastly, for a 3x3 matrix, we had this formula that's kind of complicated to memorize, but we had this little trick for figuring it out, that you write down the matrix, ADG, BEH, CFI, and then you write down the first 2 columns again. So ADG and then BEH. And then what we did was we circled all the diagonals in one direction, and we wrote little pluses here. And then we circled the diagonals in the other direction. So right here. And we have all the minuses here. We'll circle them in the other direction. We have all the minuses here, and this is how we remember what the terms are. We add AEI and BFG and CDH, and we subtract CEG and AFH and BDI. Okay, so we'll learn another method today for how to evaluate these determinants, but at least for the homework, now, well, we can see, well, these determinants are easy, right? So at least the 1x1. So the determinant of I1, it's a 1x1 matrix, just going to be 1. Exactly. And the determinant of I2, well, our formula is it's 1 times 1, right, minus 0 times 0. And so that's just going to be Sorry, so that's just going to be 1 again. Sorry, it's too much background. I need to mute. So 1 minus 0 0 is just going to be 1, and then for I3, well, let's just use this method again. 1 0 0 0 1 0 0 0 1. Now I've got to write the first 2 columns again. So I write 1 0 0 and 0 1 0. And then what do I have? I have the forward diagonals like this. So I have 1 times 1 times 1 plus 0 times 0 times 0 plus 0 times 0 times 0. And then I have the backward diagonals, which I can write this way. And so that's going to be minus 0 times 1. Sorry, if you're not answering a question, do you have a question, Gabriel? Okay, sorry, I need to mute you because there's too much background noise. So if I have 0 times 1 times 0, and then the next one is so minus 1 times 0 times 0, and then the last one is minus 0 times 0 times 1, this all ends up just being 1, right? Because all of the other terms are 0. So it turns out that the identity matrix always has determinant equal to 1, regardless of whether we're looking at the 1 by 1 identity matrix, or the 2 by 2 identity matrix, or the 3 by 3 identity matrix, right? In all cases, we get that 1 is the determinant. And it turns out that we have higher determinants. We can do something called a 4 by 4 determinant, or 5 by 5, or anything that you want. And the answer is always going to be 1. Okay. So, okay, so any questions about these computations?
Yeah, my question is,
Yeah, Rufus?
yeah, this is my question. In the process of bringing the first 2 columns outside to find the determinant,
Right.
yeah, in that process, you can decide to take the first 2 or the last 2.
No, it needs to be the first 2.
The first 2.
Needs to be the first 2. Yeah. So the last column is only written once here, and the first 2 each get written twice. Yes, it has to be first, second, third, first, second. That's the order you have to write them in.
Okay.
Yeah, otherwise, you're going to get a different answer.
Yeah, sir.
Yes, Prince.
Right. Yeah, you said always that the identity matrix will always be 1.
Yeah.
Now, in case where we have 1 times 1, and then we have the 2 times 2 to be the first identity, will it be 1 still?
Well, I mean, this is the only identity matrix. So if I put 2s in here instead, then the determinant, for instance, for the 2 by 2 identity, if instead of 1 0 0 1, I had 2 0 0 2, then the determinant would turn out to be 4, not 1. But the identity matrix is just these specific matrices. So we did these computations, and you get that the determinant is 1 always.
So again, will the number be given for the matrix, will it just be 1, or will the number change?
Oh, the numbers for matrices can change. Yeah, I mean, it's certainly other matrices can have different determinants. We're going to do some examples today, but this problem is asking about these 3 particular matrices. And so those all have determinant 1. And then there are other matrices that can have different determinants, and we're going to do a calculation today of that.
Okay, thank you.
Is that answering the question?
Yes. So Andrew?
Yes. Yep.
So with the identity matrix, the determinant always 1?
Yes. Yes, that would be true. So I'm going to write this here. So identity matrix always has determinant 1. Okay, other questions?
Thank you.
Okay, you're welcome. Okay, so let's try to talk about some new things that we have. Okay, so all right, so we already saw these screens. So I want to talk about a different way of computing 3x3 determinants, which is called expansion by minors. Okay, so here I'm just writing down the formula again. If I have any 3x3 matrix, I'm just putting the letters here to represent any possible entries, then we again have this formula for the determinant that is not very easy to memorize. Okay, so it's not so easy to memorize this formula. Okay, but I'm going to write it as in a different way that makes it a little bit easier to memorize. Okay, so what we have is I can group, I can group this term and this term together. They both have A's in them, and write that as A times EI minus FH. And I can group, I can group this term and this term together with B's, and write that as B times, it's minus BDI minus FG. So this is minus BDI and plus BFG because the minuses cancel. And then lastly, let me get another color. I can group these terms, which both have a C, and this becomes C times DH minus EG. Okay, so I have all of these, I have this different ways of writing this formula. Of course, this formula is equivalent, but my claim is that this formula is a little bit easier to remember than this formula. And I'm going to tell you why. So what we should think about this is imagine that we're walking along the top row. Okay, so we're starting at A, and then we're walking to B, and then we're walking to C. So when I have A, for instance, what I'm going to do is I'm going to look at the complementary matrix. What do I mean by the complementary matrix? I mean, if I have my entry A, so let me just write this in green. So if I have my entry A, what I mean for the complementary matrix is I cross out the row and the column that contain A, and I look at what's left.
Complementary.
Yeah. I mean, this is non-standard language. It's just what I'm calling it, this complementary matrix. So if you get rid of the A and you get rid of its row and column, what you have left is EFHI, right? It may have a name. Yeah, this could be called Sarris's rule. I don't know what the name is, but it's quite possible. And so what you do is you multiply A by the determinant of this complementary matrix. So A gets multiplied by EI minus FH, right? It's much easier to remember the determinant of a 2x2 matrix than for a 3x3, right? So if I take A times EI minus FH, that's going to be my first term here. Then I walk along. I have B. What's the complementary matrix for B? Well, I don't want to draw it. Well, maybe I'll draw it right down here. So if I want to do the complementary matrix for B, well, I have A, B, C, D, E, F, G, H, I. And if I circle B, then I can eliminate its row and its column. And the matrix that I have left is,
DF. GF.
Exactly. So DF and GI. So I get B times DI minus FG. Exactly. And then likewise, I'll just draw the same thing for C. So A, B, C, D, E, F, G, H, I. If I take C and I eliminate its row and its column, then I have this last complementary matrix right here, which is DEGH, and its determinant is DH minus EG. So I get that here. So this is one way of kind of rederiving this formula for the determinant. You walk along the top row, and in each case, you multiply the entry by the determinant of the complementary matrix. But what you have to also do is this thing that people often forget to do. You have to alternate the plus and the minus signs. Okay, so what we see here is the first term is positive, and then the second term is negative, and then the third term is positive again. Okay, so we're doing A times the determinant minus B times the determinant, and then plus C times the determinant again. And this is one way, if you can't remember this formula, that you can kind of rederive it in a way that I think is a little bit easier to remember than to memorize this big polynomial over here. Is there a question?
Yeah, yes, sir. Yeah, yes, sir.
Yes, Prince.
Yeah, thank you for demonstrating to this problem. What I see here, I think the second formula that you just brought is like difficult than the first one. In the sense that if I don't know that in the corner I got A and then I have to match with E, F, H, R. If I don't know that the second equation has all kinds of being minus, so how will I know that that's supposed to be minus? So what I think of is that the first formula is like a little bit simple than the second one that you brought.
Right. So you're always switching the pluses and the minuses. So the question is, how do you know? All right, I have to move.
That is minus.
Yeah. So let me. I'm gonna. Hold on. Yes. Sorry. I'm gonna answer that question. Okay. Let me answer that in 2 seconds. Okay. Okay. Hello. Yes.
I answer the question.
Yeah. Gabriel, you want to answer the question?
Yeah.
Sure.
Okay. My brother who saying that you don't understand whether the minus should come or plus should come. It is for the co-factor method that you determine the sign. You get me?
Yeah. Let me actually draw a picture. Here's how you remember it. What you do is you draw a little checkerboard pattern in the matrix. I mean, but you know what? Let me. I don't want to do this yet. Let me do this in 10 minutes. And then why don't we answer this question in 10 minutes? Okay. Let's answer the question 10 minutes later, because I just want to do one example first, and then we'll answer the question, and the general method will make sense. Okay. So let's do this. Let's first just do an example, right? So here's a matrix, just a random matrix to write down. So we're going to calculate it using expansion along the first row. So the last thing I want to say is that we can use any row or column to do this. So you can do this by walking along a row, or you can also do it by walking along a column. Okay, so let me just do one example in 2 ways, and then we'll answer your question about how you know when to use plus and when to use minus. Okay, so let's first do this example 2 different ways. Okay, so we're going to have first row here and the first column here. Okay. So first we're going to do the first row. Well, what do I have? I have 1 times the complementary matrix determinant is going to be 2 times 6 minus 3 times 1. Right? This is my 1, and here's my complementary matrix. So then minus, I have 3 times, then here the complementary matrix is going to be the 5, the 4, the 3, and the 6. Right? So I'm going to have 5 times 6 minus 3 times 4, and then plus 0 times the complementary matrix, which is going to be 5 times 1 minus 2 times 4. Okay, and so if we calculate this out, this becomes 1 times 9 minus 3 times, so 5 times 6 minus 3 times 4, that's 30 minus 12, so minus 3 times 18, and then plus 0 times minus 3. And all in all, this becomes, so that's 9 minus 54, so this should be minus 45. Okay. So for this determinant, we get minus 45. Okay, and let's check doing the first column instead. We're going to do the same thing, right? So I'm going to start with 1 times 2 times 6 minus 3 times 1. And then minus, now I'm walking down the first column, so I take the 5, and I take its complementary matrix. The 5, I get rid of its column and its row, and I'm left with 3, 0, 1, and 6. So it's minus 5 times 3 times 6 minus 0 times 1. And then lastly, I have plus 4 times the determinant of its complementary matrix, right? I get rid of its row and its column. So the complementary matrix is up here, 3 times 3 minus 0 times 2. And this comes out to be 1 times 9 minus 5 times 18 plus 4 times 9. And this is 9 minus 90 plus 36. And this, again, comes out to be minus 45. So I get the same answer no matter what column or row I use. Okay. So you can use any row or any column that you want, and you're always going to get the same answer. Okay, same answer no matter what column or row. But now I want to get back to Prince's question. What happens if we try to use something in the second column? Well, you still can alternate the plus and the minus signs, but you need to start with a minus. And this is the method is that when you look at your matrix, I'm going to write the following checkerboard pattern in my matrix. All right, so I write a plus in the upper left-hand corner, and then I just alternate pluses and minuses in every row and every column. So you can think of it like a chessboard, and you can think of the pluses as the white squares and the minuses are the black squares, right? This is the pattern that we're using. And if we have this method, then you use plus or minus depending on which matrix entry is being multiplied. Okay, so by the way, anybody who just came in, please remember to write your name into the chat so that we have a record of your attendance. Thank you. Okay, so what do we do? So if we wanted to use the second column, I've got my 3, 2, 1 here. So to use the second column, I'm going to have 3 times its complementary matrix. So I eliminate its column and its row. I'm left with 5, 4, 3, and 6. So it's 3 times 5 times 6 minus 3 times 4. But I have to have a negative sign here because this 3 corresponds to a minus entry over here. And now the 2 here is going to correspond to a plus entry, right? I keep alternating. So I'm going to go plus 2 times its complementary matrix. The complementary matrix of 2, right? I'm eliminating the middle column and the middle row. So what I'm left with is 1, 0, 4, and 6. So it's going to be plus 2 times 1 times 6 minus 0 times 4. And then lastly, I have the 1 over here. So the 1, I eliminate its row and its column, and I'm left with 1, 3, 0, and 5. Okay, so I then do, I'm left with 1, 3, 0, and 5. So I have minus 1, and then 1 times 3 minus 0 times 5. And so this becomes negative 3 times 18, and then plus 2 times 6, and then minus 1 times 3. And this again, this is minus 54 plus 12 minus 3. And this is again minus 45. We see we're getting the same answer no matter what column or what row we use. But we have to be careful if we use the second column that you're starting with a minus sign instead of a plus sign. And if you don't know what sign to start with, just remember, anytime you're looking at any entry in the matrix, no matter what row and no matter what column you start with, then you are always using the appropriate plus or minus sign based on this diagram. Okay? So you're always using the appropriate plus or minus sign based on this diagram, no matter what row or what column you use. So as a nice challenge exercise, You can try to do this determinant with the third column or with the second row or with the third row. These are all things we haven't done yet. And your answer should come out to be minus 45 no matter what you do. So it's this kind of amazing determinant formula where no matter what row or what column you use, you're always going to get the same answer. And this is the determinant for the matrix. Okay, any questions on this?
Yeah, sure.
Yes, Prince.
Yeah, this you use this plus minus plus. Which law are we using to derive at this plus minus plus minus plus minus and plus minus plus? Which law are we using?
So it's not a law with a name. I mean, it's really just the definition. I mean, there is an identity. I mean, what really lies behind it is that if you have this expression here, you will get this expression by using our minuses and pluses for any row or any column that you want. I don't know if this is having a name. Somebody called it Sarris's law. Maybe it's called that, but I'm actually not really familiar with the name of the law. What this is more is it's a definition. It's going to give you this quantity that we call the determinant, and then the determinant is going to have a meaning that we're going to see really more next time. We're going to see the meaning of the determinant. But using this law is what makes it so that no matter what column or row you use, you always get the same answer. If you don't do the minus pluses right, then you're going to get different answers depending on what row or column you use. So we want to get the same answer no matter what rows and columns we use. And in order to do that, you need to do these minuses and pluses in the correct pattern. So I would call it the checkerboard law or the chessboard law, but that's just my name. That's not really the real name for what this is called.
Yeah, okay. Yeah, the next question, please, can you just flip to the formula? Let's go back to the formula. I want to see something here. Yeah, okay. Okay, right here. We have A, parenthesis open ER minus FH. But then when we went to place a value, we started with -3. So you think that this formula won't confuse you because let's look at the A. The A, it just so that it's a positive. Then the value coming for it to become negative. Don't you think that there's some that confusing aspect there?
Well, the value is negative. You mean in which are you talking about on this page?
Yes, -3.
Well, because okay, because in this page we're using the second column here. So we're starting with the 3. So instead of -3, if you want to, what you should really think of it is negative of this entire thing, right? I have 3 times 5 times 6 minus 3 times 4. But I have to put a negative sign because the 3 is in a minus position, not a plus position. Right? So the 3 here is in a minus position, the 2 is in a plus position, and the 1 is in a minus position. So when I make all these terms, the 3 term gets a minus, the 2 term gets a plus, and the 1 term gets a minus. I know which pluses or minuses to use based on which position the numbers are in. So here the 3 is in a minus, the 2 is in a plus, and the 1 is in a minus.
Okay, thank you.
Does that make sense?
Yep.
Okay.
Yeah, but Andrew?
Yes.
Yeah, let me just make you understand something. Question. One, for the formula in saying that it's positive, which is to start with A and ER, because within we are looking at the first column. The first column, and the first column is 1. So we not started with the first column. We started with the second column, which if we get to the coordinate, if it's a negative. So therefore, like this is the reason why we have -3 coming outside to multiply. So it's not the first formula where you see A, we start with A, but the quadrant is positive. So you shouldn't be looking at that aspect too. Look at the first aspect is positive there.
Right, exactly. So because we're starting with B in that case. So the B, if you start with B, you have to use the negative. If you start with B or with D, then you have to use the negative. If you start with A or C or G, then you're going to use the positive. right? Because A, C, and G are in plus positions, and B and D are in minus positions. So again, you can use any row or any column you want. Let me just show you, I mean, what happens in general, right? So maybe I'll add a new page. Maybe this will clarify. So if I have my matrix A, B, C, D, E, F, G, H, I, and if I'm going to use the second column, so if I do this just in general, with my law, I'm starting with the negatives. So I'm getting minus B times DI minus FG, and then plus E times AI minus CG, and then minus H times AF minus CD, right? H, I get A, C, D, F is my matrix. If I multiply this all out, this is minus BDI minus BFG plus EAI minus ECG minus HAF plus CDH. And it turns out this is the same formula. So you can check that this is going to be the same formula. Okay, so if we do this with the minus plus minus method, then we get the same formula. This formula right out here, you can check, is going to be the same as this formula right here. You can check it in the notes, it's the same. But if you start with plus and then minus and then plus, you're not going to get the right thing. You're actually going to get the negative of this. So you're going to be off by a negative if you don't start with the minus term. Okay, so it turns out that if you start here with a minus and then a plus and then a minus, that you end up getting the same formula for the determinant. Okay, so does this answer your question?
Yeah, thank you, sir.
Okay, you're welcome. And so the point is, you can use whatever column or row you want that's going to make your life easier, right? So if there's a column that has a lot of zeros in it, then that's probably an easy column to use, because most things you're multiplying by 0, and you don't need to really worry about it. Okay. So that's determinants. So I also want to talk about the cross product today, which is going to be related to determinants. So let me recall that the dot product is defined for any two vectors of the same size. But today we're defining another type of product, which we call the cross product, which is only valid for vectors in R3. And unlike the dot product, where the result was a scalar, the cross product of two vectors is going to be another vector. Okay, so today we're going to do the formula and the rules for cross product. And next time we're going to talk about what cross product really means. And today we're also going to relate the cross product to determinants. Okay, so what's the formula for the cross product? So this is the formula right here. So if I have two vectors, A, B, C, and D, E, F, then their cross product by definition is just this third vector, which is given by this somewhat complicated formula. It's given by BF minus CE, CD minus AF, and AE minus BD as the entries. Okay, so we can do this for an example. If I want to compute the cross product of 1, 2, 3, and 4, 5, 6, well, here, this is my ABC, and this is my DEF. So I first have to do BF minus CE. So that's 2 times 6 minus 3 times 5. So I have 2 times 6 minus 3 times 5. I then do, for my second entry, I'm getting CD minus AF. So CD and AF. So this is 3 times 4 minus 1 times 6. So 3 times 4 minus 1 times 6. And then lastly, I have AE minus BD. So AE minus BD. So that's 1 times 5 minus 2 times 4. Right? So that's 1 times 5 minus 2 times 4. And this comes out to be, what does it come out to be? Well, I have 12 minus 15, so -3. And then 12 minus 6 is 6. And then 5 minus 8 is -3. Okay, so if we compute this cross product, this is what we do. But of course, the problem here is, well, this doesn't look very easy to remember, right? This is not a very easy formula to remember. Okay. So what I want to see is, what do I want to see? Okay, yeah. So this formula is not so easy to remember. But what we do see here is that the stuff here, it all looks like determinants. Okay, so this all kind of looks like determinants. Okay. And so what's going to happen is that we can actually remember this a little bit easier by using a trick that involves determinants. Okay. So this is what I'm going to show you on the next page. But before I show you, any questions about how we computed this example here?
Yes.
Yes, Princeton?
So if we are working with the cross product, is it possible that the value always in negative with two numbers? You're going to say -3, and it says half positive, and the other half negative.
Yeah,
So
you
also
can have
compulsory that everything can end negative.
If all of your elements are positive, then that's a good question. That's a good question. Is it possible that the cross product of two vectors with all positive entries can consist of something with all negative entries? I think the answer is yes. Yeah, the answer is yes. If you have to, I think it is possible that you can have two entries where two vectors where everything is positive and their cross product is all negative. So yeah, the positive and negative signs in the cross product are very unintuitive. We don't have good rules about, taking products of positive things gives you positive things, or taking products of negative things gives you negative things. The rules that actually get you these entries are kind of unintuitive. There aren't good rules about it. Okay. Good. Other questions? You're welcome.
Hello?
Yes, Rufus.
Yeah, the process of selecting the pattern, does it fit to say, it is false for you to say, you start from the middle by saying beta f bf minus e times ce. Instead, in case I decide to say, we'll start with this pattern, by saying a times f is af and c times d is cd. With that arrangement coming down, and the next one by saying beta d bd, and the next one is eta EAE.
Right.
Yeah, will it be the same as the same pattern that you arrange?
Yeah, I think so, right? I mean, yeah, what you've said is the same as the pattern that I have here.
So the order of selecting the pattern does not matter.
Well, I mean, okay, no, you have to select the BF minus CE has to be first. And then the CD minus AF has to be next. And then the AE minus BD has to be next. Yeah, so you do have to have this first, and then this second, and then this third.
Okay.
Yeah. So let me
Andrew?
Yes, Princeton.
Yeah, Princeton. Yeah, so it tell me that the other matter here within the cross product, other matter.
Yeah, so there's another method that I'm going to show you. Yeah. Okay. So this is the method. And so this method's not so easy to remember. So this next method shows kind of why this makes sense, why it's not just random. So I first need a little notation. So you'll sometimes see this in physics books or in math books. So we have three special vectors in R3 that are just the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And sometimes we give these vectors names. We call them I, J, and K, right? So this is I, this is J, and this is K. Okay, so we get these vectors are special enough that we give them names. They're kind of like, they're the vectors that everything is built out of. So this, I realize I messed up. I should say, so if I have two vectors A, B, C, and D, E, F, what does it mean to write the determinant of this matrix? Well, it's a little bit weird, right? Because the determinant of this matrix, I mean, these are scalars and these are vectors, right? So it's kind of, I need to put it in scare quotes here, right? Because it's not, we didn't define the determinant with vectors. We only defined it with numbers. But if you bear with me here, then let me show you what happens if we just try to do this. So what I'm going to do is I'm going to use expansion along the first row. So if I do it this way, what do I get? I get I times BF minus CE, and then minus J times, well, I get rid of the column in the row. I have AF minus CD. And then plus K times, what's the complementary matrix? AE minus BD. Right? Or in other words, how can I write this vector? Well, this is a sum of a bunch of vectors times a bunch of scalars, right? So, but the point is, if I have some scalar times I plus some scalar times j plus some scalar times k, then what happens is this scalar just becomes the first coordinate. And this scalar becomes the second coordinate. And then this scalar becomes the third coordinate. So I just get BF minus CE here. Then here I get, well, I don't have AF minus CD because there's a minus sign. So I actually get CD minus AF. And then lastly, for the third coordinate, I get AE minus BD. And if you look at this over here, it's exactly the same formula that we have for the cross product. Okay, so this is the same as the cross product formula. Okay.
Yeah, but Andrew?
Yes, Princeton.
Yeah, my question about due to the second either the way get negative J, which is the vector AF minus CD. So with the quality of the formula within the parenthesis here, you brought CD and then minus AF. So why we can multiply the negative that is attached by the AF, which will be negative AF, then we multiply negative by negative, which should be the positive CD. Instead of you bringing the CD first and the AF going last.
Oh, I just do that because I don't like. Yeah, I just don't like starting with negatives. So if you wanted to write this as negative AF plus CD, that would be fine. That's equivalent. I just think that this looks cleaner. So I always think if I have a subtraction and then I negate it, I always think of that as just reversing the order of the subtraction because I think it usually looks nicer. But if you want to, instead of this, if you want to write minus AF plus CD, that's absolutely okay. And it's equivalent.
So if it be like that, if the value is given, so will the answer be the same?
Yeah, it'll be the same.
If you are okay.
Yeah. And so what we see here is that, so this is the same as the cross product formula. So the reason these determinants or these things are all showing up is that it actually just comes from this determinant, right? The cross product of A, B, C, and D, E, F can be thought of as just taking the determinant of this matrix where you start with I, J, K, and then you write A, B, C in the next row, and then you write D, E, F in the row after that. Okay. And so this is maybe easier to remember than this formula over here. So you just have to remember, oh, it's going to be this determinant, and I'll do it by expanding along the first row. Okay. And that, I think, for a lot of people is going to be easier than memorizing the formula for cross product. Okay, so the conclusion is that the cross product can be thought of as a determinant. So cross products and determinants are kind of two aspects of the same thing. Okay. And so what I want to say, so we're basically out of time for today, but what I want to say is next time we're going to have the geometry of cross product of cross product and determinant, meaning what do they mean? Right? I mean, in both of these lectures, all I did was I said, okay, here's some formula for the determinant, and here's some formula for a cross product of two vectors. But I mean, anybody can make up formulas, right? The only reason they're worth studying is because they actually have some sort of meaning. And so this meaning is what we're going to talk about next time. And so maybe you've seen, if you've studied some physics, cross products sometimes show up when you're calculating torque and when you're calculating kind of rotational motion and things like this. But one of the things that it means, so just a preview, and then I'll stop, is that if I take the vector v and I cross it with a vector w, this is a vector that is perpendicular to both v and w. So if I take a vector v and I take its cross product with a vector w, then the resulting vector is perpendicular to both of them. So this is a check that you can do with our example. You can check that, where are we? No, sorry. Here. So you can check that in this example, the cross product is minus 363. You can check that it's perpendicular to both 1, 2, 3 and to 4, 5, 6. Remember how we check perpendicularity? You take the dot product and see that it's 0. That means that the two vectors are perpendicular. Okay, so you can check that if you take the dot product of this with 1, 2, 3, it's going to be 0. And if you take the dot product of this with 4, 5, 6, it's also going to be 0. So part of the meaning of cross product is that you get a vector. It's a way of getting a vector that's perpendicular to both of your original vectors. Okay, so it has a real geometric meaning. Okay, so there will be, since we have 3 weeks, there's going to be 4 homework assignments this week. So the first 2 are straightforward, just to evaluate a determinant and evaluate a cross product. And then 3 and 4 are about showing some properties of the cross product. So first you want to show that if v is a vector and c is a scalar, then if you take the cross product with v and some multiple of v, some cv, that you're always going to get the 0 vector. So if I take 1, 2, 3, and I take its cross product with 2, 4, 6 with its double, then I always end up with the 0 vector. And then lastly, the exercise 4 is to show that if I have 2 vectors v and w, that if I take their cross product, it's the same. If I switch the order of the cross product, then I actually get the negative. So this means that the cross product is not commutative. So if I take 2 vectors and get a certain cross product, if I take the same cross product of the 2 vectors, but I put them in the opposite order, then I'm going to end up getting the negative. I'm not going to get the same result. Right? So it's not like a usual product where it doesn't matter what order you use. Right? For the cross product, the order matters, because if you switch the order, you're going to get a negative answer. Okay? So these are all for the homework. Highly encourage you to work on the homework, because, I mean, none of these questions takes that long to do, and you do have a while before the next thing, so before the next class. So if you want to send your homework to the WhatsApp or to my email, which is andrewobis@gmail.com, I'm always happy to look at your homework. And yeah, so just to review, so Merry Christmas to everybody, Happy New Year, and remember that there will be no meetings on December 23rd or December 30th. That's for Christmas and for New Year's. So there's going to be no meetings those days. So the next meeting will be January 6th, and we're going to discuss the geometry of determinants and cross products. And one last reminder to please type your name if you have not done so. so that we have a record for the attendance. Okay. Okay, so any questions from anyone? Okay, no questions?
Yeah, thank you for the class today, Doc. There's no major question.
Okay, you're welcome, Miata. Thank you for coming.
All right, thank you.
Okay.
Thank you, Andrew. Thank you so much.
All right, you're welcome, Sangay. So yeah, so just remember for the data. Yes, happy holidays, everyone. Yes. And so just remember for the data, Sangay, that there's no distribution for the next 2 weeks.
Okay.
Okay, great. All right. Okay, everybody, have a great weekend, a great holiday season, and a happy new year.
Thank you so much.
You see the same.
Okay, and I'll send out the notes and the recording later today.
Thank you, Andrew.